For most of human history, asking how big the universe is sounded like a philosophical question, not a scientific one. You could count stars, map galaxies, even estimate distances between them. But the idea of a total size felt out of reach. The universe didn't come with edges, rulers, or markers, telling us where it ends. Then things changed, not all at once, and not because someone finally spotted a cosmic wall. It changed because scientists learned how to turn light into a time machine, how to read the expansion of space itself, and how to use faint radiation left over from the early universe as a measuring tool. Over decades, these pieces slowly locked together. Today, cosmologists can put real numbers on the size of the observable universe. Not guesses, not poetic descriptions. Actual distances, calculated using physical laws, precise observations, and models that match what we see in the sky. Even more surprising, they can also place limits on how large the entire universe must be beyond what we can see. That doesn't mean we now know where the universe ends, or even if it ends at all. But it does mean the question, how big is the universe, is no longer vague. It has become a technical problem with answers that are strange, unintuitive, and far larger than most people expect. To understand how scientists reach those numbers, we have to be very clear about what they measured, what they didn't, and what size actually means when space itself is expanding. When scientists talk about the size of the universe, the first thing they have to do is narrow the meaning of the word universe. Not because they want to avoid the bigger question, but because physics forces them to. The term they use is the observable universe, and it has a very specific definition that's easy to misunderstand. The observable universe is not everything that exists. It's everything that can, in principle, be observed from Earth today, using light or any other signal that travels at or below the speed of light. That limitation isn't philosophical. It's physical. Information takes time to travel, and the universe has only existed for a finite amount of time. That single fact immediately puts a boundary on what we can see. The universe is about 13.8 billion years old. That number comes from multiple independent measurements, but the exact value isn't the point here. What matters is that light has had only 13.8 billion years to move through space. Anything farther away than light could have reached us from since the beginning simply hasn't had time to send a signal. No telescope, no matter how powerful, can get around that. So the observable universe is defined by a horizon, not a physical wall, not an edge you could fly into, but a limit set by time and speed. Beyond that horizon, light exists, matter exists, galaxies exist, but their signals haven't arrived here yet. That sounds simple, but there's a complication that makes this boundary much larger than most people expect. If space were static, the observable universe would be a sphere with a radius of about 13.8 billion light-years. Light starts somewhere, travels for 13.8 billion years, reaches us, end of story. But space isn't static. It's expanding, and it has been expanding the entire time that light has been traveling. That means the galaxies that emitted the oldest light we can see are not sitting 13.8 billion light-years away today. They were much closer when that light was emitted. While the light was in transit, space stretched. The distance between us and the source increased, even though the light kept moving forward locally at the speed of light. This is why astronomers make a distinction between light travel time and current distance. Light travel time tells you how long the signal has been on the way. Current distance tells you how far away the source is now after billions of years of cosmic expansion. When scientists define the observable universe, they use current distance, not light travel time. That's why the observable universe has a radius of about 46 billion light-years, not 13.8. The light took 13.8 billion years to arrive, but the space between us and the source stretched during that journey. So the observable universe is a sphere centered on Earth with a radius of roughly 46 billion light-years, containing everything whose light has had time to reach us since the beginning of cosmic expansion. This immediately raises an uncomfortable question. Why is Earth at the center? The answer is that it isn't, at least not in any meaningful sense. Every observer, anywhere in the universe, has their own observable universe centered on their own location. An observer in a galaxy 10 billion light-years away would see a different region of space with a different set of galaxies, bounded by their own cosmic horizon. There is no preferred center. The center exists only because observation requires a point of view. This is one of the hardest ideas to internalize because we're used to thinking of boundaries as shared. A country has borders everyone agrees on. A planet has a surface everyone can see. The observable universe doesn't work like that. Its boundary is personal, defined by where you are and how long the universe has existed. Another key point: the observable universe is not shrinking or growing in the way objects usually do. As time passes, light from more distant regions reaches us, so the observable universe expands. But that expansion slows over time because of how cosmic expansion behaves. There are also regions that are expanding away from us so quickly that light emitted there today will never reach us, even in the infinite future. Those regions are already beyond our event horizon. That's why scientists are careful with language. The observable universe is what we can see now, not everything we will ever see. Within this observable universe are all the galaxies, clusters, filaments, voids, radiation fields, and background signals we can measure. Every map of the cosmos, no matter how deep, samples only this region. When telescopes look farther back in time, they're still looking within the same observable boundary, just at earlier stages of cosmic history. This definition also explains why the observable universe looks the way it does. The most distant light we see isn't coming from stars or galaxies at all. It comes from a nearly uniform glow called the cosmic microwave background, released when the universe was hot, dense, and opaque, about 380,000 years after expansion began. That radiation marks the farthest surface we can observe directly. It forms a shell around us the same in all directions, defining the deepest observational limit. Beyond that surface, the universe existed, but it was filled with plasma that scattered light constantly. No photons from earlier times could travel freely. So even though the universe is older than the cosmic microwave background, it is not optically observable beyond it. That distinction matters because it shows that observable doesn't just mean far away. It means physically able to send us information. Some regions are unobservable because they're too distant. Others are unobservable because the early universe itself blocked signals. The observable universe, then, is not just a distance limit, it's an information limit. This is also why the observable universe is not a fixed catalogue of objects. As telescopes improve, we don't expand the observable universe by brute force. We fill it in with more detail. The boundary remains the same, but our understanding of what's inside becomes richer. Another common misunderstanding is the idea that the observable universe contains most of the universe. There is no evidence for that. In fact, all available measurements suggest the opposite. The observable universe is almost certainly a tiny fraction of the total universe. The reason is geometry. Measurements of large-scale curvature show that space is extremely close to flat. In cosmology, flatness doesn't mean infinite by definition, but it strongly suggests that if the universe is finite, it must be vastly larger than what we can observe. Even small curvature would be detectable if the universe wrapped around on scales comparable to the observable region. It doesn't. So when scientists define the observable universe, they are not quietly claiming it's all there is. They are drawing a boundary around what physics allows us to access. There's also an important distinction between observable and visible. Some parts of the observable universe are technically within the horizon, but still difficult or impossible to detect directly, because their signals are too faint, absorbed, or redshifted beyond practical limits. The observable universe is defined by principle, not by current technology. Even with perfect instruments, we could never observe beyond this boundary, because the signals simply aren't here. This is why the phrase edge of the universe is misleading. The observable universe has an edge, but the universe itself may not. That edge isn't a location you could reach. If you travel toward it, the horizon would move with you. New regions would become observable ahead of you, while regions behind you would drop out of view for observers elsewhere. In other words, the observable universe is not embedded in space like a bubble. It's a relationship between time, distance, and the speed of light. Defining it this way is not a limitation of imagination. It's a strength of modern cosmology. By being precise about what can and cannot be observed, scientists avoid making claims they can't test. The observable universe becomes a well-defined laboratory governed by measurable laws. Everything we know about cosmic history, expansion, structure formation, and large-scale behavior comes from studying this region. All claims about the universe's size, age, and contents begin here. So when scientists say they have calculated the size of the observable universe, they are not claiming to have measured infinity or found the universe's edge. They are stating something much more careful and much more powerful. Given the laws of physics and the age of the universe, there is a maximum region from which information could have reached us, and its size can be calculated. That definition is the foundation for everything that follows. When scientists give a number for the size of the observable universe, they are not estimating, rounding loosely, or speaking metaphorically. They are reporting a calculated distance based on well-defined measurements and a specific way of describing space. The result is precise, but the path to that number is not intuitive. Today, the observable universe has a radius of about 46 billion light-years, which means a diameter of roughly 92 billion light-years. That single statement sounds straightforward, but it only makes sense once you understand what kind of distance is being measured and why simpler definitions don't work. The key idea is something called co-moving distance. This is the distance between 2 points in the universe measured in a coordinate system that expands along with space itself. In other words, it factors out the ongoing expansion and asks, if we could freeze the universe's expansion at this moment, how far apart would these locations be? Astronomers use co-moving distance because ordinary distance doesn't behave normally on cosmic scales. If you tried to define distance as how long light has been traveling, you would get a completely different and misleading answer. Light from the most distant regions of the observable universe has been traveling for about 13.8 billion years, but those regions are not 13.8 billion light-years away today. They are much farther. To see why, imagine light leaving a distant galaxy shortly after the universe became transparent. At the moment of emission, that galaxy was relatively close. While the light traveled toward us, space itself expanded. The light kept moving locally at the speed of light, but the distance it still had to cross kept increasing. By the time the light arrived here, the source galaxy was no longer anywhere near its original position in terms of present-day distance. This means that the universe has effectively stretched the path the light traveled while the light was already on its way. To account for this, cosmologists don't ask, how long did the light travel? They ask, how far away is the place where that light came from now? That question leads directly to the 46 billion light-year figure. The calculation starts with the age of the universe and the measured expansion history of space. Scientists know how fast the universe has been expanding at different times, because they can observe galaxies at many different distances and see how their light has been stretched or redshifted. This redshift acts as a record of expansion. Using this information, cosmologists build a mathematical model that describes how the scale of the universe changes over time. Once that expansion history is known, they can track how far a photon travels as space expands beneath it. Integrating that process from the moment the photon was emitted to the present gives the co-moving distance. When this is done for the oldest light we can observe, the cosmic microwave background, the result is a co-moving radius of about 46 billion light-years. It's worth stressing that this number is not arbitrary or controversial. Different teams using different datasets and methods converge on essentially the same value. Small variations exist, depending on the exact cosmological parameters used, but they are measured in fractions of a billion light-years, not tens of billions. The size of the observable universe is therefore one of the most robust numbers in cosmology. Another important detail is that the observable universe is spherical, not because the universe itself is spherical, but because light reaches us equally in all directions. No matter where we look, we see roughly the same cosmic horizon distance. That symmetry tells us something important. On large scales, the universe is remarkably uniform. The radius of 46 billion light-years applies in every direction. There is no direction in which the observable universe is significantly larger or smaller. This isotropy is one of the pillars of modern cosmology. Now, a common question is why the number is so much larger than 13.8 billion. Even people familiar with astronomy often expect the observable universe to be about 14 billion light-years across, not over 6 times that in radius. The confusion comes from assuming that space behaves like a static backdrop. In everyday experience, if something has been traveling for 10 years at a fixed speed, it must be 10 light-years away. But that logic fails when the medium through which the object travels is itself expanding. In the universe, light does not simply move through space. It moves with space while space stretches underneath it. Early in cosmic history, the expansion rate was much higher than it is today. This means that much of the stretching happened while the light was still in transit. As a result, the most distant observable regions have receded far beyond what light travel time alone would suggest. There is also an important distinction between two types of horizons: the particle horizon and the event horizon. The 46 billion light-year radius corresponds to the particle horizon, the maximum distance from which light has already had time to reach us. The event horizon, by contrast, marks the maximum distance from which light emitted now will ever reach us in the future. Because the expansion of the universe is accelerating, the event horizon is actually smaller than the particle horizon. There are galaxies within the observable universe today that we will never receive new light from beyond a certain point in time. This does not change the size of the observable universe as defined today, but it does highlight that the observable universe is not simply everything we'll ever see. Another subtle point is that the observable universe is not a rigid boundary. As time passes, the particle horizon grows. Light from regions that were once just beyond our reach eventually arrives. In that sense, the observable universe slowly expands. However, this growth is asymptotic. Because of accelerated expansion, the rate at which new regions become observable slows down over time. The observable universe will never include everything that exists, even in the infinite future. When scientists quote the size of the observable universe, they are usually referring to its present-day co-moving radius. That choice allows meaningful comparisons across time. A co-moving coordinate assigned to a galaxy today will still describe the same galaxy billions of years from now, even though its proper distance will have changed. This is why cosmological maps are often labeled in co-moving megaparsecs rather than light years. The numbers look different, but the concept is the same. Converting units, 46 billion light-years corresponds to roughly 14,000 megaparsecs. That scale encompasses hundreds of billions of galaxies, each containing billions of stars. Even then, this vast region is only the observable portion. Another misconception is that the observable universe contains all matter that currently exists within that radius. In reality, what we observe is a time slice that becomes older with distance. Nearby galaxies are seen as they are now. Distant galaxies are seen as they were billions of years ago. The farthest observable regions are seen as they existed shortly after the universe became transparent. So when we say the observable universe has a certain size, we are not describing a snapshot of the universe at a single moment in cosmic time. We are describing a layered structure of past states, arranged by distance. Despite this complexity, the size itself remains well defined. The particle horizon today marks a sphere centered on the observer with a fixed co-moving radius. Everything inside that sphere has contributed information to us. Everything outside has not. It's also important to understand that the 46 billion light-year radius is not something you could measure by physically traveling outward. Even if you moved at nearly the speed of light, the expansion of space would constantly reshape which regions are within your horizon. The boundary is not something you can approach or reach. From a different galaxy, the observable universe would still have a radius of about 46 billion light-years, but it would include a different set of galaxies. Some objects we can see would be outside their horizon, and some objects they can see are outside ours. This reinforces the idea that the observable universe is not a fixed object embedded in space. It's a consequence of location, time, and cosmic expansion. The precision of this size estimate depends on how well we know the universe's expansion history. Improvements in measurements of cosmic background radiation, galaxy distributions, and large-scale structure have steadily refined the number. But the general scale has been known for years, and it has remained stable as data quality improved. That stability is significant. It tells us that the underlying cosmological model used to calculate the observable universe's size is not fragile. Small changes in parameters do not radically alter the result. So when headlines say scientists have calculated the size of the universe, what they are usually referring to is this specific, carefully defined quantity, the current co-moving diameter of the observable universe. It is not a guess, and it is not the full story, but it is a real physical size that can be calculated, checked, and refined. And once that size is established, it becomes the baseline for every deeper question about how much larger the universe might be, beyond what we can see. For most of human history, the universe didn't have a measurable size because distance itself wasn't something people could extend beyond the solar system in any reliable way. The night sky looked flat. Stars appeared pinned to a dome. Even when early astronomers understood that planets moved differently from stars, there was no method to tell how far away any of it was. The first real step toward measuring cosmic distance came from geometry, not technology. Ancient Greek astronomers understood parallax in principle, the apparent shift of an object's position when viewed from different locations. But Earth-based instruments weren't precise enough to detect stellar parallax. The stars were simply too far away. That failure wasn't a setback. It was an early clue that the universe was vastly larger than anyone had imagined. It wasn't until the 19th century that stellar parallax was finally measured. By observing nearby stars at opposite points in Earth's orbit around the Sun, astronomers could detect a tiny angular shift against the background of more distant stars. This allowed the first direct distance measurements beyond the solar system. The distances were staggering by historical standards, measured in trillions of kilometers. But even then, the method only worked for stars that were relatively close by on a galactic scale. Parallax defined the first rung of what later became known as the cosmic distance ladder. Each rung depended on the previous one. You could measure parallax for nearby stars, then use those stars to calibrate other methods that worked farther out. The next major advance came with variable stars, especially Cepheid variables. These stars pulse in brightness with a regular period, and crucially, the period is directly related to their intrinsic luminosity. By measuring how fast a Cepheid pulses, astronomers can determine how bright it truly is. Comparing that to how bright it appears from Earth gives a distance. This discovery transformed astronomy in the early 20th century. Cepheids could be seen far beyond the immediate neighborhood of the Sun, deep into the Milky Way, and even into nearby galaxies. For the first time, astronomers had a way to measure distances on intergalactic scales. That's when the picture of the universe began to change fundamentally. In the 1920s, Edwin Hubble used Cepheid variables to show that certain fuzzy patches in the sky were not gas clouds within the Milky Way, but entire galaxies far outside it. This immediately expanded the known universe by orders of magnitude. The Milky Way went from being the universe to just one galaxy among many. But Hubble's most important contribution came next. When he compared the distances to galaxies with their spectral redshifts, he found a clear relationship. The farther away a galaxy was, the faster it appeared to be moving away from us. This was not just a new distance measurement. It was the discovery that the universe is expanding. Before this, distance was thought of as static. Galaxies were assumed to sit in space like islands in a fixed ocean. Hubble's observation showed that space itself was stretching. Distance was no longer a simple geometric quantity. It was dynamic. Hubble's law gave astronomers a new way to estimate distances. Redshift. The light from distant galaxies is stretched as space expands, shifting it toward longer wavelengths. By measuring this shift, astronomers could infer how fast the galaxy is receding. With a known expansion rate, that recession speed could be converted into distance. This was a radical shift. Distance was no longer measured directly through geometry or brightness alone. It was inferred through the behavior of space itself. Early measurements of the expansion rate were crude. Hubble's original value was off by nearly an order of magnitude, but the concept worked. As instruments improved, the expansion rate was refined, and redshift became a central tool for mapping the universe. Still, even with redshift, astronomers were limited to relatively nearby galaxies by modern standards. To go farther, they needed brighter markers. This led to the use of Type Ia supernovae. These stellar explosions occur when a white dwarf star reaches a critical mass and detonates in a predictable way. Because the underlying physics is consistent, these supernovae have nearly uniform intrinsic brightness. That makes them excellent standard candles. Type Ia supernovae can be seen across billions of light years. By the late 20th century, they extended the cosmic distance ladder deep into the observable universe. They also delivered a surprise. The expansion of the universe is accelerating. This discovery, made independently by two teams in the late 1990s, forced astronomers to rethink not just distance measurement, but the future of cosmic expansion itself. It introduced dark energy into cosmological models and added a new layer of complexity to calculating distances across cosmic time. At this point, distance measurement had become inseparable from cosmology. You could no longer talk about how far away something was without specifying the model of the universe you were using. Meanwhile, another line of evidence was emerging that would anchor cosmic distances even more firmly: the cosmic microwave background. This faint radiation, discovered in the 1960s, is the afterglow of the early universe, released when the universe cooled enough for light to travel freely. It provides a snapshot of the universe at a very specific moment, about 380,000 years after expansion began. The cosmic microwave background is not just a background glow. Its tiny temperature variations encode information about the geometry, composition, and expansion history of the universe. By analyzing these patterns, scientists can infer the universe's overall curvature and scale. This was a turning point. Distance measurements were no longer based solely on local calibrations that accumulated uncertainty with each rung of the ladder. They were tied to global properties of the universe itself. Satellites designed to measure the cosmic microwave background with high precision allowed cosmologists to determine key parameters: the age of the universe, its matter content, and its expansion rate. Once those parameters were known, distances on the larger scales could be calculated consistently. By the early 21st century, cosmology had become a precision science. Different methods, parallax, variable stars, supernova, redshift surveys, and background radiation were all pointing to a coherent picture. This convergence mattered because it reduced ambiguity. Distance estimates derived from entirely different physical phenomena agreed with each other within narrow margins. That consistency gave scientists confidence that they weren't just fitting models to limited data, but actually capturing how the universe works. As a result, astronomers could now do something that would have been impossible a century earlier: calculate the size of the observable universe by integrating the expansion history of space itself. Importantly, this was not done by measuring outward step by step until reaching a boundary. Instead, scientists reconstructed how distances evolved over time. They asked how far light could have traveled given the universe's age and expansion rate at every stage of its history. This approach sidestepped the need for direct measurement at the larger scales. It relied on understanding physical laws and applying them consistently. The history of cosmic distance measurement is therefore not a story of bigger telescopes alone. It's a story of better calibration, deeper physical understanding, and tighter connections between theory and observation. Each step depended on the previous one being reliable. Parallax anchored Cepheids. Cepheids anchored galaxies. Galaxies anchored redshift surveys. Supernovae extended the scale. The cosmic microwave background locked the whole structure into place. What changed over time was not just how far we could see, but what distance meant. It evolved from a simple geometric idea into a quantity that depends on time, expansion, and cosmic history. By the time scientists began seriously discussing the size of the observable universe, they were no longer extrapolating wildly beyond known territory. They were extending a framework that had been tested repeatedly at smaller scales. This is why modern size calculations carry weight. They are not speculative leaps. They are the end result of more than a century of refining how distance itself is defined and measured. The universe did not suddenly become measurable. Distance became something physics could describe, and once distance could be described reliably, the question of cosmic size stopped being philosophical and became mathematical. One of the most common mistakes people make when thinking about the universe's size is imagining galaxies flying outward through empty space, like shrapnel from an explosion. That picture feels natural because it matches everyday motion, but it's also wrong in a very specific and important way. On cosmic scales, galaxies are not primarily moving through space. They are being carried apart by space. This distinction between motion through space and the expansion of space itself is central to how scientists calculate distances and, ultimately, the size of the observable universe. When astronomers observe distant galaxies, they see that their light is redshifted. The usual explanation is that the galaxies are moving away from us. That's true in a limited sense, but it hides the deeper mechanism. Most galaxies are not speeding away because they were flung outward. They are separating because the fabric of space between us and them is stretching. To understand why this matters, it helps to start small. Inside galaxies, stars orbit normally. Inside galaxy clusters, galaxies move under gravity. On these scales, space is effectively static. Expansion does not pull the solar system apart or stretch atoms. Gravity and other forces dominate. But on very large scales, tens or hundreds of millions of light years, gravity weakens and expansion wins. Beyond those scales, the dominant behavior of the universe is not motion through space, but the growth of space itself. This is why cosmologists use a different mathematical description for large-scale motion. Instead of treating galaxies as objects moving in a fixed background, they describe the universe with a metric that changes over time. Distances grow because the scale of space increases. In this framework, galaxies can be nearly at rest in their local coordinates, while still becoming more distant from each other. Their separation increases not because they're traveling, but because the ruler used to measure that separation is getting longer. A helpful analogy is dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart. None of the dots are moving across the surface. The surface itself is expanding. The dots simply go along for the ride. The analogy isn't perfect. Space isn't a surface expanding into a higher dimension, but it captures the essential point. Expansion is not something happening in space. It is something happening to space. This difference becomes critical when interpreting redshift. In ordinary motion, redshift is a Doppler effect. A source moves away and the waves stretch. In cosmic expansion, the wavelength of light stretches because the space it travels through stretches. For nearby galaxies, these two effects are almost indistinguishable. But for very distant galaxies, the Doppler interpretation breaks down. The redshift becomes too large to explain as simple motion through space without violating relativity. Instead, the correct picture is that light is being stretched continuously as it moves through expanding space. The longer the journey, the more stretching occurs. This is why some galaxies appear to be receding faster than the speed of light. That statement sounds impossible, but it's only impossible if you assume motion through space. Expansion of space itself is not limited by the speed of light. Relativity restricts how fast objects can move locally through space, not how fast space can expand globally. When astronomers say a galaxy has a recession speed greater than the speed of light, they are not claiming the galaxy is breaking physical laws. They are describing how quickly the distance between us and that galaxy is increasing due to expansion. This distinction has direct consequences for how we define and calculate cosmic distances. If galaxies were simply flying outward through space, then light travel time would map cleanly to distance. But because space expands, distance becomes a time-dependent quantity. At the moment a photon is emitted, the source galaxy has one distance. While the photon is traveling, that distance changes. By the time the photon arrives, the distance is larger. So when scientists ask how far away something is, they have to specify when. This leads to several different distance measures in cosmology: proper distance, co-moving distance, luminosity distance, angular diameter distance. Each one answers a different question and behaves differently over time. The size of the observable universe depends specifically on co-moving distance, because it allows scientists to compare locations across cosmic history without the answer changing simply because the universe expanded. If you misunderstand expansion as motion, this choice makes no sense. But once expansion is understood as a property of space itself, co-moving distance becomes the natural way to describe size. Another important implication involves horizons. In a static universe, the horizon would simply be a shell defined by how far light has traveled. In an expanding universe, horizons are more complex. They depend on how the expansion rate changes over time. Early in cosmic history, expansion was extremely rapid. This means that some regions were carried away from us faster than light could close the gap, even though light was moving at its maximum speed locally. Later, expansion slowed, allowing light from some of those regions to eventually reach us. This dynamic behavior is why the observable universe is larger than the light travel distance would suggest. It's also why some regions that exist today will never be observable, no matter how long we wait. None of this makes sense if you imagine galaxies simply moving through a fixed space. The entire structure of cosmology depends on treating space as an evolving entity. This framework also explains why there is no center of expansion. In an explosion, there's a point where everything started. In cosmic expansion, every point sees other points moving away. The expansion happens everywhere, not from anywhere. This is not just philosophical. If there were a center, it would show up in observations as an asymmetry. One direction would look different from another. But observations show that, on large scales, the universe looks the same in all directions. That uniformity only works if expansion is happening to space itself. The difference between motion and expansion also resolves a common confusion about why distant galaxies don't slow down as gravity pulls them back. On very large scales, gravity from matter is too weak to halt expansion. The expansion is not a force pushing galaxies outward, it's a change in the underlying geometry. Once galaxies are separated beyond a certain scale, they are no longer gravitationally bound. Their increasing separation is not something gravity needs to overcome. It's the default behavior of the expanding universe. This perspective also clarifies why local systems remain intact. The solar system does not expand. Atoms do not expand. The Milky Way does not expand internally. Expansion only becomes significant where the density of matter is low enough and distances are large enough. In practical terms, this means that the expansion of space cannot be detected with a ruler or a laboratory experiment. It reveals itself only through the collective behavior of distant objects over vast distances. For size calculations, this is essential. The observable universe is not measured by imagining a ruler laid out across space. It is calculated by tracking how space itself has grown over time. Every photon we receive carries a record of that growth. Its wavelength tells us how much space expanded while it was traveling. By collecting and interpreting those records across the sky, scientists reconstruct the expansion history of the universe. Once that history is known, the distinction between motion and expansion becomes more than a conceptual point. It becomes the foundation for every large-scale distance calculation. Without it, the 46 billion light-year radius of the observable universe would be inexplicable. With it, that number is not only reasonable, it is unavoidable. Understanding this difference is what allows cosmology to move beyond naive pictures and treat the universe as a physical system governed by precise laws. And it's why calculating the universe's size is not about tracking objects moving through space, but about understanding how space itself evolves. The story of the universe's size cannot be told without confronting a period that rewrote every intuitive expectation about scale: cosmic inflation. Without inflation, many of the numbers scientists use today would not only be hard to explain, they would make no sense at all. Inflation refers to a brief but extreme phase of expansion that occurred very early in the universe's history, long before galaxies, stars, or even atoms existed. This was not the steady expansion we observe today. It was something far more violent. For a tiny fraction of a second, space expanded exponentially, doubling in size again and again at an extraordinary rate. This idea did not come from speculation about size. It emerged from a set of deep problems in early cosmology that had nothing to do with distance measurements at first glance. One of those problems was uniformity. When scientists began studying the cosmic microwave background in detail, they found something puzzling. No matter which direction they looked, the universe appeared almost exactly the same. The temperature of the background radiation varied by only tiny fractions of a degree across the entire sky. That shouldn't have been possible in a simple Big Bang model without inflation. Regions on opposite sides of the observable universe are so far apart that, in a non-inflationary universe, they would never have been able to exchange information or energy. There would have been no time for them to come into thermal equilibrium. And yet, they look nearly identical. This is known as the horizon problem. Inflation solves it cleanly. Before inflation, the universe was much smaller, small enough that all the regions we now see across the observable universe were once close together and causally connected. They had time to interact, exchange energy, and smooth out differences. Inflation then rapidly stretched this small, uniform region to enormous scales, freezing in that uniformity. Another problem inflation addresses is flatness. Observations show that the geometry of space is extremely close to flat. In cosmological terms, this is not the default outcome. A universe that starts even slightly curved tends to become more curved over time. Inflation changes that behavior. Exponential expansion drives space toward flatness, much like inflating a balloon makes its surface look flatter over small regions. The more inflation occurs, the closer space appears to perfectly flat. This matters for size because flat geometry places strong constraints on how large the universe must be. A universe that appears this flat over the observable region must be far larger than that region, possibly vastly larger. Inflation was proposed in the early 1980s as a theoretical mechanism to resolve these and other issues. But it quickly became more than a patch. It made specific, testable predictions. One of those predictions involved tiny fluctuations. Inflation does not produce a perfectly smooth universe. Quantum fluctuations present during inflation get stretched to macroscopic scales. These fluctuations become the seeds of all later structure: galaxies, clusters, and cosmic filaments. When scientists measured the cosmic microwave background with increasing precision, they found exactly the pattern inflation predicted. The temperature variations were small, nearly scale invariant, and statistically uniform across the sky. This was a major success. Inflation was no longer just a theoretical convenience. It became part of the standard cosmological framework. Once inflation is accepted, the question of the universe's size changes fundamentally. Inflation does not just make the universe large, it makes it potentially enormous, far larger than the observable universe and possibly infinite in extent. The observable universe becomes just a tiny patch within a much larger whole. Importantly, inflation does not necessarily tell us the total size of the universe. What it does is set a minimum scale. The amount of inflation determines how much larger the universe must be compared to what we can see. Observations of flatness and uniformity imply that inflation lasted long enough to stretch space by an immense factor. Even conservative estimates suggest the universe is at least hundreds of times larger than the observable region. Some models imply it is exponentially larger. This is where the phrase real size becomes tricky. Inflation makes it clear that the observable universe is not representative of the whole. It is a limited sample carved out of a much larger structure. Another crucial aspect of inflation is that it decouples size from age in a way that is not intuitive. The universe can be only 13.8 billion years old and still be far larger than 13.8 billion light-years in extent, even ignoring ongoing expansion. During inflation, space expanded so rapidly that distances grew faster than light could traverse them, not because light was violated, but because expansion itself has no speed limit. This created enormous separations in an extremely short time, and after inflation ended, the universe transitioned into a more familiar expansion regime governed by radiation, then matter, and eventually dark energy. But the scale set during inflation never went away. It became the baseline on which all later expansion built. This means that when scientists calculate the size of the observable universe today, they are not just integrating expansion back to the Big Bang. They are integrating back to a universe that already underwent a dramatic inflation-driven enlargement. Without inflation, the observable universe would be much smaller, and many of its observed properties would be inexplicable. With inflation, the numbers line up. Inflation also introduces a subtle but profound implication. The universe beyond our observable region may not be uniform in the same way. While inflation smooths out space locally, different regions may have experienced slightly different inflationary histories. Some inflationary models suggest that inflation never fully ends everywhere. Instead, it continues in some regions, constantly creating new pockets of space. This leads to the idea of eternal inflation and a vast, possibly infinite cosmic structure containing many regions like ours. Whether or not eternal inflation is correct, the key point is that inflation breaks the intuitive link between what we can see and what exists. The observable universe is no longer assumed to be a typical or complete representation of the whole. From a size perspective, inflation shifts the goalposts. Instead of asking, how big is the universe? Scientists ask, how large must it be given what we observe? That question can be answered partially. The observed flatness of space implies a lower bound on the universe's size. If the universe was smaller than that bound, curvature would be detectable across the observable region. It isn't, so inflation turns observational absence into quantitative constraint. The fact that we do not see curvature or large-scale irregularities tells us that the universe must extend far beyond what we can observe. Another consequence of inflation is that it explains why the observable universe has a well-defined horizon at all. Without inflation, the early universe would have been causally fragmented in a way that makes the current horizon difficult to interpret. Inflation creates a coherent causal structure that later expansion stretches. This is why the observable universe has a meaningful size rather than being an arbitrary cutoff. It reflects the interplay between inflation, expansion, and the finite speed of light. Inflation also affects how scientists interpret claims about measuring the universe's size. No measurement of the observable universe's diameter can ever reveal the total size if inflation occurred. At best, it can set limits. That's why modern discussions about the universe's real size are careful. They do not claim to have found an edge or boundary. They claim to have constrained possibilities. Inflation is the reason those constraints are meaningful. Before inflation, the universe could plausibly have been just slightly larger than the observable region. After inflation, that possibility is essentially ruled out. The universe must be much larger, even if we cannot say exactly how much larger. This has practical consequences for cosmological modeling. When scientists simulate the universe, they do not model the entire thing. They model a representative volume large enough to capture relevant behavior. Inflation justifies this approach by making the observable universe statistically typical of a much larger whole, at least on large scales. At the same time, inflation warns against assuming too much. Just because our region looks uniform and flat does not mean all regions are identical. From a measurement standpoint, inflation introduces a permanent ceiling on what can be known. No matter how advanced our instruments become, no matter how long we observe, we will never see beyond the inflation-stretched horizon that encloses our observable universe. The universe's true size may be finite or infinite. Inflation allows for both. What it does not allow is a universe that is only marginally larger than what we can see. So when scientists talk about calculating the universe's size today, they are doing so in a post-inflationary framework. Every number, every distance, every horizon is interpreted through the lens inflation provides. The observable universe's immense size is not surprising in this context. It is expected. What would be surprising is if the universe ended just beyond our observational reach. Inflation makes that scenario extremely unlikely. In that sense, inflation doesn't just explain why the universe is large, it explains why the observable universe is not the whole story, and why any attempt to define the universe's real size must begin with the assumption that what we see is only a small part of something much bigger. Hubble's law is one of those ideas that sounds simple until you realize how much work it's doing behind the scenes. At face value, it says this: the farther away a galaxy is, the faster it appears to be receding from us. That relationship is not a coincidence, and it's not just a descriptive trend. It's the backbone of how cosmic distances are translated into numbers. The law is usually written as a short equation. Recession speed equals distance multiplied by the Hubble constant. But that compact form hides several layers of meaning. It's not a law about galaxies speeding away from Earth specifically. It's a statement about how expansion operates everywhere in the universe. When Edwin Hubble first discovered this relationship in the late 1920s, he did not set out to measure the universe's size. He was comparing distances to galaxies, measured using Cepheid variable stars, with their redshifts. What he found was that redshift increased steadily with distance. At the time, this was interpreted as galaxies moving away through space. That interpretation has since been refined, but the relationship itself held up. The farther the galaxy, the larger the redshift. The cleaner the data became, the tighter the line appeared. The slope of that line is the Hubble constant. Despite the name, it is not truly constant in time. It is the current expansion rate of the universe. As the universe evolves, this value changes, but at any given moment, it defines how distance and recession speed relate. Today, the Hubble constant is measured in units that sound awkward at first, kilometers per second per megaparsec. What this means is that for every megaparsec of distance, about 3.26 million light-years, the apparent recession speed increases by a fixed number of kilometers per second. If the Hubble constant was 70 kilometers per second per megaparsec, a galaxy 1 megaparsec away would appear to recede at 70 kilometers per second. A galaxy 10 megaparsecs away would recede at 700 kilometers per second. A galaxy 1,000 megaparsecs away would recede at 70,000 kilometers per second. This linear scaling is what makes Hubble's law so powerful. Once you know the expansion rate, redshift becomes a distance indicator. But there's a catch. Redshift does not measure distance directly. It measures how much the wavelength of light has been stretched. To turn that stretching into a distance, you need a model of how the universe has expanded over time. For nearby galaxies, this is straightforward. Their redshifts are small, and the expansion rate, has not changed much during the light's journey. In that regime, Hubble's law works almost like a simple ruler. For distant galaxies, things get more complicated. The expansion rate was different when the light was emitted. Matter dominated early on, then dark energy began to dominate later. The Hubble constant today is not the same as it was billions of years ago. So cosmologists distinguish between the Hubble constant as a present-day value and the Hubble parameter as a function of time. Calculating distances across the observable universe requires integrating this changing expansion rate over cosmic history. This is why measuring the Hubble constant accurately is such a big deal. Any uncertainty in its value propagates into uncertainty in distances, ages, and sizes. Over the past few decades, scientists have measured the Hubble constant using multiple independent methods. One approach builds outward from the cosmic distance ladder, using parallax, Cepheids, and supernovae to calibrate distances to galaxies, and then linking those distances to redshifts. Another approach starts at the other end of time. It uses the cosmic microwave background to infer the expansion rate indirectly, based on conditions in the early universe and how they evolve under known physical laws. These two methods currently produce slightly different values for the Hubble constant. This discrepancy is known as the Hubble tension. It is one of the most closely studied problems in cosmology today. Importantly, this tension does not overturn the basic use of Hubble's law. The disagreement is on the order of a few percent, not orders of magnitude. Both methods agree that the universe is expanding and that distance and redshift are tightly linked. For calculating the size of the observable universe, this level of uncertainty matters, but it does not undermine the result. A small change in the Hubble constant shifts the calculated radius slightly, but the overall scale remains tens of billions of light years. Hubble's law also explains why the observable universe has a horizon in the first place. As distance increases, recession speed increases. Beyond a certain distance, the recession speed exceeds the speed of light, not because galaxies are moving locally that fast, but because the space between us is expanding rapidly. Light emitted beyond a certain point can never overcome this expansion. It is carried away faster than it can make progress toward us. That defines the event horizon. The particle horizon, the boundary of the observable universe today, is related but distinct. It depends on how expansion behaved in the past, not just now. But Hubble's law is embedded in both concepts because it governs how distance evolves with time. Another subtlety is that Hubble's law applies only on large scales. Nearby galaxies can deviate from it because of local gravitational effects. The Andromeda Galaxy, for example, is moving toward us, not away. This does not contradict expansion. It simply means local gravity dominates over cosmic expansion on small scales. When scientists calculate the size of the observable universe, they deliberately avoid these local complications. They work in a regime where Hubble's law is clean and the universe behaves uniformly. This is why surveys that map millions of galaxies across billions of light years are so valuable. They smooth out local motions and reveal the underlying expansion pattern with high precision. Hubble's law also underpins the use of redshift as a proxy for time. Because light from more distant galaxies has been traveling longer, higher redshift generally means earlier cosmic time. This allows astronomers to reconstruct the expansion history by observing galaxies at different redshifts. By stitching together these observations, scientists build a timeline of how the expansion rate has changed. That timeline feeds directly into calculations of distance and size. It's important to emphasize that Hubble's law does not say the universe has a center. Every observer sees the same pattern. Galaxies recede faster the farther away they are. An observer in a distant galaxy would see us moving away at a speed proportional to our distance from them. This symmetry is another reason Hubble's law is interpreted as expansion of space, not motion through space. If galaxies were flying away from a central point, the pattern would look different from different locations. Because Hubble's law is linear and universal, it allows cosmologists to treat the observable universe as a coherent system. Distances scale predictably. Redshifts encode expansion. Horizons emerge naturally. Without Hubble's law, there would be no clean way to connect observation to size. The universe's expansion would be a qualitative statement, not a quantitative tool. With it, cosmologists can take measurements of light stretching and convert them into distances that reflect how space itself has evolved. This is why any claim about the universe's size rests, at some level, on Hubble's law. Even when more sophisticated models are used, they reduce to refinements of this basic relationship. The law does not tell us where the universe ends. It does not tell us whether it ends at all. What it does tell us is how to translate what we see into a scale. And once you have that scale, the observable universe stops being an abstract idea and becomes a region with a measurable size, defined by expansion, governed by physics, and anchored by a simple but profound relationship discovered nearly a century ago. The cosmic microwave background, often shortened to CMB, is the most important single observation for fixing the universe's large-scale size. Unlike galaxies or supernova, it does not belong to any one location in space. It surrounds us in every direction, acting as a reference surface against which cosmic distances can be anchored. The CMB is radiation released when the universe was about 380,000 years old. Before that time, the universe was hot, dense, and filled with charged particles. Photons could not travel freely because they were constantly scattered by electrons. Space was opaque. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen. This sudden change allowed light to move freely for the first time. The radiation released at that moment has been traveling ever since, stretched by expansion from visible and infrared wavelengths into microwaves. That radiation did not originate from a single place. It was emitted everywhere at once. What we observe today is a spherical shell centered on us, representing the farthest distance from which light could have reached us since the universe became transparent. This shell is sometimes called the surface of last scattering. It is not a physical wall, it is a time boundary. It marks the transition between an opaque early universe and a transparent one. The distance to this surface defines the deepest observational limit of the universe. No matter how powerful a telescope becomes, it cannot see beyond this point using light. That makes the CMB an ideal reference for measuring the size of the observable universe. But the real power of the CMB lies not in its existence, but in its structure. At first glance, the CMB looks almost perfectly uniform. Its temperature is nearly the same in every direction, differing by only a few parts in 100,000. This uniformity reinforces the idea that the universe is isotropic and homogeneous on large scales. However, those tiny temperature variations are not noise. They are the imprints of density fluctuations in the early universe. Regions that were slightly denser or slightly hotter left a measurable mark on the radiation. These fluctuations form a detailed pattern across the sky. When scientists analyze that pattern, they extract precise information about the universe's geometry, composition, and expansion history. One of the most important features in the CMB is a characteristic angular scale associated with sound waves in the early universe. Before the CMB was released, matter and radiation were tightly coupled, behaving like a fluid. Pressure waves, essentially sound, traveled through this plasma. The maximum distance those sound waves could travel before the universe became transparent is well understood from basic physics. That physical size acts like a known ruler embedded in the early universe. When we observe the CMB today, we see that ruler projected onto the sky. Its apparent angular size depends on the geometry and expansion history of the universe. If the universe was strongly curved, that ruler would appear larger or smaller than expected. If the expansion history were different, the projection would change. By measuring the angular size of this feature with high precision, scientists can determine the universe's spatial curvature. The result is striking. Space is extremely close to flat. This flatness has direct implications for size. In a flat universe, distances add up in a way that allows the observable universe to be very large without introducing detectable curvature across the region we can see. The CMB also allows scientists to measure the universe's age. The pattern of fluctuations depends sensitively on how long the universe expanded before releasing the radiation. This provides an independent way to fix the timeline. Once the age and geometry are known, the distance to the surface of last scattering can be calculated accurately. That distance is essentially the radius of the observable universe. Importantly, this calculation does not rely on galaxies, stars, or supernovae. It uses early universe physics that is well understood and testable in laboratories. That makes the result robust. The distance to the CMB surface is not measured directly. It is inferred by fitting cosmological models to the observed pattern of fluctuations. But those models are tightly constrained. There is very little freedom to change the outcome without breaking agreement with data. This is why the CMB plays such a central role in claims about the universe's size. It anchors the largest distances in a way that does not depend on extrapolating from local measurements alone. Another advantage of the CMB is that it covers the entire sky. Galaxy surveys sample specific regions. Supernovae are sparse and unevenly distributed. The CMB is everywhere. This all-sky coverage allows scientists to test for large-scale anisotropies. If the observable universe had an irregular shape or a preferred direction, it would show up in the CMB. No such large-scale deviations are observed. The uniformity of the CMB in all directions supports the assumption that the observable universe is roughly spherical and that its boundary is at the same distance, no matter where we look. The CMB also informs the expansion history after its release. The way its fluctuations evolve and are distorted by later cosmic structure reveals how space expanded over time. This helps refine the conversion between redshift and distance. In practical terms, when cosmologists calculate the 46 billion light-year radius of the observable universe, the CMB is doing much of the heavy lifting. It sets the far boundary and locks in the geometry needed to interpret distances. Without the CMB, estimates of the universe's size would rely far more heavily on extrapolations from galaxies and supernova, increasing uncertainty. With it, the larger scale becomes one of the best constrained. There is also a deeper conceptual role. The CMB marks a universal reference time. Every observer anywhere in the universe would see their own CMB shell centered on them, corresponding to the same cosmic moment. This reinforces the idea that the observable universe is defined by physics, not by observational technology or human perspective. The CMB also clarifies why the observable universe has a sharp limit. Beyond the surface of last scattering, the universe existed, but it was opaque. Light from earlier times cannot reach us because it never traveled freely. So the size of the observable universe is not just a consequence of distance and expansion. It is also a consequence of transparency. The universe had to become see-through before observation was possible. This detail matters because it shows that the observable universe is not equivalent to the particle horizon at all wavelengths. In principle, other messengers like neutrinos or gravitational waves could probe earlier times. But even then, there would still be fundamental horizons. For light-based observations, the CMB is the ultimate boundary. The precision with which the CMB has been measured means that the size of the observable universe is not something that will change dramatically with future data. Refinements will happen, but the scale is set. This is why discussions about the universe's real size often begin with the CMB. It provides the clearest, most comprehensive picture of how big our observable patch of the cosmos really is. Everything beyond that patch remains hidden, not because it doesn't exist, but because the universe itself placed a limit on what light could ever reveal. Dark energy enters the story of the universe's size not as a speculative add-on, but as a measured effect that changes how distances evolve over time. Without accounting for dark energy, calculations of cosmic expansion would not match what astronomers actually observe. The existence of dark energy was inferred from observations of distant Type Ia supernovae in the late 1990s. These supernovae appeared dimmer than expected, meaning they were farther away than a universe with constant or slowing expansion would allow. The only consistent explanation was that the expansion of the universe has been speeding up. Acceleration immediately changes how size is interpreted. In a universe dominated by matter alone, expansion slows over time. Gravity gradually pulls things back, even if it never fully reverses expansion. In such a universe, the observable region grows steadily as light from ever more distant regions reaches us. Dark energy alters that trajectory. It causes the expansion rate to increase, which has a direct impact on which regions of the universe are observable and which are not. The simplest model of dark energy treats it as a constant energy density associated with space itself. As space expands, the total amount of this energy increases rather than diluting. This creates a persistent push that counteracts gravity on large scales. From a distance measurement perspective, this means that the relationship between redshift and distance is not fixed. The same redshift corresponds to different distances, depending on how dominant dark energy was during the photon's journey. This is why dark energy must be included in any calculation of the observable universe's size. Ignoring it would produce a universe that is systematically too small. Dark energy also introduces the concept of a cosmic event horizon in a more serious way. Because expansion is accelerating, there are regions that are currently observable but will eventually disappear from view in the sense that no new information from them will ever reach us. Light emitted from those regions today will never arrive here. The space between us and them expands too quickly for the light to make net progress toward us. This does not affect the current size of the observable universe, which is defined by past light that has already arrived, but it does affect the future evolution of observability. Over time, the observable universe will asymptotically approach a fixed size. New regions will be added at a slower and slower rate. Eventually, the observable universe will stop growing in any meaningful sense. This is a direct consequence of dark energy. Another important effect of dark energy is on co-moving distances. Co-moving coordinates factor out expansion, allowing scientists to compare positions across time. Dark energy changes how these coordinates relate to proper distances, especially at late times. When cosmologists integrate the expansion history to calculate the particle horizon, dark energy contributes significantly to the result. It increases the total co-moving distance that light could have traveled compared to a universe without acceleration. This is one reason the observable universe's radius is so large. If the universe had remained matter-dominated, the horizon would be smaller. Dark energy also affects how scientists interpret large-scale structure. As acceleration increases, the growth of cosmic structures slows. Galaxies stop clustering efficiently beyond certain scales. This freeze-out influences how uniform the universe appears at the largest distances. That uniformity, in turn, reinforces the assumptions used in size calculations. A highly clumped universe would complicate interpretations of distance and curvature. Dark energy smooths things out on the larger scales. Another subtle role of dark energy involves curvature constraints. Observations show that space is very close to flat. Dark energy helps maintain that flatness over time by dominating the energy budget and preventing curvature from becoming dynamically important. This again feeds back into size estimates. A flat universe can extend far beyond the observable region without introducing detectable geometric distortions. Dark energy also separates the concepts of age and size more dramatically. In a decelerating universe, there is a tighter link between how long the universe has existed and how far light could have traveled. In an accelerating universe, that link loosens. The universe can be relatively young and still have an enormous observable size because early expansion and later acceleration stretch distances in different ways. This is why naive calculations based on age alone fail. Dark energy reshapes the entire expansion curve. Importantly, dark energy does not create new observable regions. It actually does the opposite in the long run. By accelerating expansion, it ensures that many regions will forever remain beyond reach. From the standpoint of measuring the universe's size, dark energy sets a hard limit on what can ever be known observationally. No future technology can overcome an accelerating metric. This also means that claims about the universe's real size must be framed carefully. Even if the universe is finite, its full extent may be permanently inaccessible. Dark energy is not just a late-time detail. Its effects accumulate. Even small differences in its strength or behavior would produce noticeable changes in horizon size. This is why modern cosmological models test dark energy parameters against multiple datasets. The observable universe's size is one of the constraints those models must satisfy. Another consequence is that dark energy introduces sensitivity to assumptions. Different models of dark energy, constant, slowly evolving, or dynamic, can slightly alter distance calculations. However, current data strongly favors a simple, nearly constant form. Within that framework, the size of the observable universe remains stable across models. Dark energy also changes how scientists think about the future observable universe compared to the past one. The universe was more observable in the past in the sense that new regions were continuously entering the horizon. That process is now slowing. In the far future, distant galaxies will fade from view as their light becomes increasingly redshifted. The observable universe will become emptier, not because objects vanish, but because expansion isolates regions from one another. This has no impact on the current size calculation, but it emphasizes that the observable universe is a dynamic concept shaped by expansion physics. Dark energy ensures that the observable universe has a finite informational content. There is a maximum amount of cosmic history that can ever be accessed. From a size perspective, dark energy does not define the boundary, but it locks it in. When scientists calculate the observable universe's size today, they do so knowing that this number is not just a snapshot. It is a consequence of the universe's long-term behavior. Without dark energy, the observable universe would be smaller today and larger in the future. With dark energy, it is large now and bounded forever. That makes dark energy a central ingredient in any serious discussion of how big the universe is and how much of it can ever be known. The Dark Energy Survey, usually shortened to DES, was designed to answer a deceptively simple question. How fast is the universe expanding, and how has that rate changed over time? While it was not built specifically to measure the universe's size, its results feed directly into how large the observable universe must be. DS began as a response to a growing realization in cosmology. By the early 2000s, scientists knew that dark energy dominated the universe's expansion, but they did not know its precise properties. Small uncertainties in dark energy parameters translated into large uncertainties when distances were extrapolated across billions of light-years. If the goal was to calculate the universe's scale precisely, those uncertainties had to be reduced. DES tackled this problem by surveying a large fraction of the southern sky with a single, carefully calibrated instrument. The idea was not to look deeper than any telescope before it, but to look wider, more uniformly, and with tighter control over systematic errors. Over several years, DES mapped hundreds of millions of galaxies extending out to distances of several billion light-years. This was not just a cataloguing effort. Every galaxy's position, shape, and brightness carried information about how space had expanded and how matter was distributed. One of DES's core techniques was weak gravitational lensing. As light from distant galaxies travels toward us, it passes through regions filled with matter. Gravity subtly bends the light, distorting the apparent shapes of background galaxies. These distortions are tiny. You cannot see them by looking at individual galaxies. But when averaged over millions of galaxies, they reveal the large-scale distribution of matter in the universe. Why does this matter for size? Because the growth of structure depends on the expansion history. If expansion were slower, gravity would have more time to clump matter together. If expansion were faster, structure growth would be suppressed. By measuring how clumped matter is at different distances, DES effectively reconstructed how expansion behaved over time. Another key probe used by DES was baryon acoustic oscillations, often abbreviated as BAO. These are the same early universe sound waves imprinted in the cosmic microwave background, but observed later in the distribution of galaxies. In the early universe, sound waves traveled through hot plasma, leaving behind a characteristic scale. That scale acts as a standard ruler. When astronomers measure how that ruler appears at different redshifts, they can infer how distances scale with time. DES detected this feature in the spatial distribution of galaxies across its survey volume. This provided an independent check on distance measurements derived from other methods. DES also observed thousands of Type Ia supernovae, extending the supernova distance ladder with a uniform dataset. Because the same instrument and calibration pipeline were used throughout, systematic uncertainties were reduced. Each of these probes, weak lensing, galaxy clustering, supernova, has its own sensitivities and weaknesses. What made DES powerful was that it combined them within a single framework. If one probe pointed to a particular expansion history, while another disagreed, the model would fail. Consistency across all probes was required. This cross-checking is critical when claims about the universe's size are involved. A size calculation based on one dataset alone can be misleading. Agreement across independent methods strengthens confidence. DES results showed that the expansion history inferred from large-scale structure is consistent with a universe dominated by dark energy behaving very much like a constant energy density. There was no strong evidence for exotic deviations. This matters because distance calculations depend heavily on the assumed behavior of dark energy. If dark energy varied significantly over time, co-moving distances to the cosmic horizon would shift. DES helped narrow the allowed behavior of dark energy, reducing the range of possible expansion histories compatible with observations. Another contribution of DES was tightening constraints on the universe's matter density. The amount of matter affects how quickly expansion slowed in the past and how fast it accelerated later. Matter density feeds directly into the calculation of the particle horizon. A higher matter density leads to a different expansion curve than a lower one. By pinning down this parameter more precisely, DES reduced uncertainty in horizon size estimates. DES also played a role in testing the flatness of the universe. The combination of galaxy clustering and lensing is sensitive to spatial curvature. A curved universe would distort distance relationships in measurable ways. DES data supported the conclusion that space is very close to flat. This reinforced conclusions drawn from the cosmic microwave background but using completely different physics and observational scales. This independent confirmation is important. If both early universe and late universe observations point to flatness, the conclusion is hard to avoid. Flatness implies that the observable universe is not a special geometric feature. It is a small patch of a much larger space. From the perspective of calculating size, DES did not dramatically change the numerical value of the observable universe's radius. That number was already well established. What DES did was shrink the error bars. Before surveys like DES, there was more flexibility in cosmological models. You could tweak parameters slightly and still fit existing data. With DES, many of those tweaks became incompatible with observations. This matters because claims about the universe's real size often hinge on how much freedom remains in those models. Tight constraints mean fewer loopholes. DES also helped clarify the relationship between local measurements of expansion and global ones. While it did not resolve the Hubble tension on its own, it provided a bridge between early universe measurements and late universe structure growth. Understanding this relationship is crucial because the observable universe's size depends on integrating expansion across the entire history of the universe, not just measuring it at one moment. DES results showed that within uncertainties, the large-scale expansion history is consistent with the values needed to produce a particle horizon of about 46 billion light-years. In other words, there was no hidden mismatch suggesting the observable universe should be significantly larger or smaller. Another subtle contribution of DES lies in how it handled systematic uncertainty. Measuring cosmic size is not limited by statistical noise. It is limited by calibration errors, selection biases, and modeling assumptions. DES was designed with this in mind. The survey invested heavily in understanding detector behavior, atmospheric effects, and data processing artifacts. This attention to detail improved confidence in derived distances. That confidence carries over into horizon calculations. When distances to galaxies at different redshifts are trustworthy, integrating expansion becomes less speculative. DES also demonstrated the power of large, homogeneous datasets. Rather than combining many small surveys with different biases, DES offered a unified view of a large cosmic volume. This uniformity matters because the observable universe's size is a global property. Patchy or inconsistent data can distort inferences. Another outcome of DES was reinforcing the idea that the observable universe's scale is not sensitive to small parameter shifts. Even when cosmological parameters are varied within allowed ranges, the horizon size remains large. This stability is important when communicating results. It means that claims about the universe's size are not hanging on a knife edge. DES also influenced how future surveys are designed. It demonstrated that mapping large-scale structure with high precision is not only possible, but essential for refining cosmological measurements. Upcoming surveys build directly on DES methods, aiming to reduce uncertainties further. But the basic picture DES supports is unlikely to change dramatically. From a conceptual standpoint, DES moved cosmology further away from speculative territory and deeper into precision science. The universe's expansion history is no longer loosely sketched. It is charted in detail across most of cosmic time. This detailed expansion history feeds directly into how far light could have traveled and how much space has expanded since then. In that sense, DES is part of the reason scientists can now speak confidently about the observable universe's size without hedging every statement. DS also helped clarify what claims about real size can and cannot mean. The survey does not reveal the universe's total extent. It constrains the parameters that any total size must respect. If the universe were only slightly larger than the observable region, certain signatures would appear in large-scale structure. DES does not see them. This absence becomes evidence. It tells scientists that the universe must be much larger than what we observe, consistent with inflationary expectations. The Dark Energy Survey therefore occupies an important middle ground. It does not rely on early universe relics like the cosmic microwave background, and it does not rely solely on nearby distance ladders. It probes the universe at intermediate epochs where dark energy becomes dominant. By doing so, it stitches together the expansion story from early times to the present. That stitching is essential for size calculations. Without it, the observable universe's scale would be less secure. DES shows how measuring the universe's size is not about one dramatic discovery, but about accumulating constraints from many directions until the numbers have nowhere left to go. The result is not a dramatic revision of cosmic scale, but a tightening of what was already known. And in cosmology, that tightening is what turns bold claims into solid ones. In recent years, headlines have increasingly claimed that scientists have finally calculated the universe's real size. That phrasing is catchy, but it hides what the actual scientific claims are doing. No one has discovered an edge, measured a boundary, or mapped the universe beyond what we can see. What has changed is something more subtle and more technical. The new claims are about constraints, not direct measurements. When researchers talk about the universe's real size today, they are usually referring to new analyses that combine multiple datasets, cosmic microwave background measurements, galaxy surveys, gravitational lensing data, and inflationary models to place stronger lower bounds on how large the universe must be beyond the observable region. This is an important shift. Earlier cosmology could say the universe was at least as large as what we can see. Modern cosmology can say it must be much larger than that, and can quantify how much larger. The most common form of these claims comes from studies of spatial curvature. If the universe was small and closed, wrapping back on itself at scales comparable to the observable universe, that curvature would leave detectable signatures. Light would take multiple paths. Patterns in the cosmic microwave background would repeat or distort. Large-scale galaxy distributions would deviate from flat predictions. These effects have not been observed. Recent analyses push the allowed curvature closer and closer to zero. In practical terms, this means that if the universe is finite, its radius of curvature must be far larger than the observable universe. Some studies translate this into statements like, the universe must be at least hundreds of times larger than the observable region. That is where real size language enters the picture. Another source of these claims comes from refined inflationary modeling. Inflation predicts that the observable universe occupies a small patch of a much larger spacetime. By comparing inflationary predictions with precise measurements of cosmic fluctuations, researchers can rule out inflation scenarios that produce only minimal enlargement. What survives are models where inflation lasted long enough to make the total universe vastly larger than what we see. In some cases, scientists express this as a minimum number of times the observable universe could fit inside the whole universe. These numbers are not guesses. They are derived from limits imposed by data. It is crucial to understand what these results are not saying. They are not saying the universe has a known finite size. They are not saying it has been measured end to end. They are not even saying it is definitely finite. They are saying that, given how flat and uniform the observable universe is, the total universe cannot be only slightly larger than what we can see. Some of the strongest claims come from looking for repeating patterns in the cosmic microwave background. In a small, closed universe, light could wrap around and produce matching temperature patterns in different directions. Extensive searches for such correlations have found none. The absence of these patterns translates into size constraints. If the universe wraps around, it must do so on scales much larger than the observable horizon. Another line of research examines large-angle anomalies and correlations in the cosmic microwave background. While some features have been debated, none provide convincing evidence of a compact universe. When models are fit carefully, they favor large or infinite spatial extent. Galaxy surveys contribute as well. A universe with a small global size would affect how structures form and repeat. The lack of observed repetition or cutoff effects in large-scale structure pushes size limits upward. Some recent papers combine all of these observations into a single statistical framework. Instead of asking whether the universe is flat or curved, they ask how much curvature is allowed before it conflicts with data. The answer is very little. That very little curvature corresponds to a universe whose total size, if finite, dwarfs the observable region. This is where popular summaries often oversimplify. Saying scientists calculated the real size of the universe sounds definitive. What scientists actually calculated are lower bounds that are now so large they feel almost equivalent to infinity for practical purposes. In everyday language, saying something is at least 250 times bigger than what we can see sounds like a size measurement. In scientific terms, it's a constraint. Another important detail is that these results depend on assuming the correctness of the standard cosmological model. That model has passed many tests, but it is still a model. If some aspect of gravity, dark energy, or inflation behaves differently on ultra-large scales, the conclusions could change. Researchers are explicit about this in technical work. The universe's real size is always conditional on assumptions. The improvement is that those assumptions are now tightly tested. What has changed in the last decade is not a breakthrough observation, but a tightening of uncertainty. Earlier, cosmologists could not rule out a universe only a few times larger than the observable region. Now, those possibilities are strongly disfavored. This shift allows scientists to speak more confidently about scale, even while acknowledging ignorance about the total extent. Another driver behind these claims is improved statistical power. Modern datasets are large enough that cosmic variance, the fact that we only observe one universe, can be modeled more rigorously. This allows researchers to say what would be unlikely to observe if the universe were small. When those unlikely signatures fail to appear, size limits increase. Some analyses also explore exotic topologies, universes that are finite but wrap in complex ways. These too leave signatures. Their absence further constrains possibilities. It's worth noting that different papers report different minimum sizes, depending on how conservative the assumptions are. Some state lower bounds of tens of times the observable universe. Others reach hundreds or more. The exact number is less important than the trend. The trend is that every new dataset pushes the minimum size upward, not downward. This is why claims about finally calculating the universe's size are misleading, but not entirely baseless. Scientists are not finding the size. They are fencing off what the size cannot be. From a scientific perspective, that is meaningful progress. Another reason these claims gain traction is that the observable universe's size is now so well established that attention naturally shifts beyond it. Once one number stabilizes, curiosity moves to the next unknown. But unlike the observable universe, the total universe does not offer a clean calculation. It offers a set of possibilities constrained by physics. Recent work has made those possibilities narrower. There is also a communication gap between technical language and public language. In technical terms, saying the universe must be at least X times larger than the observable universe at 95% confidence is precise but clunky. In headlines, that becomes scientists calculated the universe's real size. The science itself is careful. The translation is not. Importantly, none of these studies claim that future observations will reveal the full universe. They explicitly acknowledge that regions beyond the observable horizon are causally disconnected. The universe could be finite or infinite, and we may never know which. What we do know is that if it is finite, it is not small. These new claims also reinforce inflationary expectations, rather than challenge them. Inflation predicted a universe much larger than what we can see. The data increasingly support that picture. So Section 10 is not about a single discovery, paper, or number. It is about a convergence of evidence that allows scientists to say, with increasing confidence, that the observable universe is a tiny fraction of the whole. Calling that the universe's real size stretches the phrase beyond its technical meaning. But behind the phrase is a genuine scientific advance, the shrinking of uncertainty about how small the universe cannot be. That is what has actually been calculated. Not the universe's edge, but the minimum scale of its vastness. When scientists talk about the minimum size of the entire universe, they are doing something very different from measuring the observable universe. They are not pointing telescopes outward and finding a boundary. They are asking a conditional question. how large must the universe be in order for the observable region to look the way it does? That question can be answered quantitatively. The most direct way to set a minimum size comes from spatial curvature. In cosmology, curvature describes whether space is flat, positively curved like a sphere, or negatively curved like a saddle. A universe that is positively curved is finite. A flat or negatively curved universe can be infinite. If the universe is finite and curved, its curvature radius sets a natural size scale. A small universe would have noticeable curvature across the observable region. A large universe would look flatter. Observations show that the observable universe is extremely close to flat. The deviation from flatness is constrained to be tiny. This immediately implies that if the universe is finite, its radius of curvature must be much larger than the observable universe. To turn this into a size estimate, cosmologists use the measured limits on curvature and ask how large a closed universe would need to be for that curvature to remain undetectable across a region 46 billion light-years in radius. The answer is very large. Depending on the confidence level and the dataset used, studies find that the universe must be at least tens to hundreds of times larger than the observable universe in radius. In terms of volume, that translates into millions or billions of observable universe volumes. These are not speculative numbers pulled from theory alone. They are derived from fitting cosmological models to data and ruling out smaller sizes that would produce observable effects. And one way to understand this is to imagine living on the surface of a very large sphere. If the sphere is small, its curvature is obvious. Straight lines curve back on themselves. Triangles have angles that don't add up the way you expect. Now, if the sphere is enormous compared to your local neighborhood, everything looks flat. You would have to travel vast distances to detect curvature. The observable universe is our local neighborhood. The fact that it looks flat to high precision means the underlying sphere, if it exists, must be enormous. Another approach to setting minimum size comes from searching for topological signatures. A finite universe does not just curve, it can also wrap around in complex ways. Light could travel around the universe and reach us from multiple directions, producing repeating patterns. Extensive searches have been conducted for such repetitions, especially in the cosmic microwave background. Researchers look for matching temperature patterns or correlations that would indicate light circled the universe. The absence of such signatures sets a lower limit on the size of any possible wraparound dimension. Those limits again push the minimum size far beyond the observable horizon. Large-scale structure surveys provide additional constraints. In a small universe, the distribution of galaxies would reflect the finite size. Certain wavelengths of density fluctuations would be suppressed or enhanced. No such anomalies are observed. Instead, the distribution of matter appears consistent with a universe that extends far beyond the surveyed region. These independent lines of evidence reinforce each other. Curvature constraints, topology searches, and structure formation all point to the same conclusion. If the universe is finite, it is much larger than what we can observe. And it's important to emphasize that these are minimum sizes, not estimates of the true size. There is no upper bound. The universe could be thousands, millions, or infinitely many times larger than the observable region. The minimum size also depends on assumptions. Most calculations assume the standard cosmological model with general relativity, dark energy behaving like a constant, and inflation producing nearly scale-invariant fluctuations. Within that framework, the limits are robust. Changing assumptions can shift the numbers, but only within a restricted range unless the model is radically altered. Another subtlety is the difference between linear size and volume. Saying the universe is 100 times larger could mean 100 times the radius or 100 times the volume. Most technical papers refer to radius or characteristic length scale. A universe 100 times larger in radius than the observable universe would be 1,000,000 times larger in volume. This distinction often gets lost in popular summaries. Minimum size estimates also evolve as data improve. Early limits allowed relatively small closed universes. As measurements became more precise, those possibilities were eliminated. This trend has been consistent. Each generation of data has increased the minimum allowed size, not decreased it. That pattern matters because it suggests the limits are not fluctuating wildly. They are converging toward the conclusion that the observable universe is a very small fraction of the whole. Another consequence of these limits is that they make some theoretical models less plausible. Certain cosmological models predict small or moderately sized universes. Those models are now strongly constrained or ruled out. At the same time, models that allow extremely large or infinite universes remain compatible with data. Observations cannot distinguish between very large and infinite. This leads to an important conceptual point. When scientists say the universe is at least a certain size, they are not implying it is close to that size. They are stating a floor, not a target. The true size could be unimaginably larger. These minimum size estimates also help clarify why the observable universe looks statistically smooth. In a small universe, fluctuations would be limited by the size of the space. In a very large universe, fluctuations can exist on scales far larger than what we observe, making our patch appear uniform. Inflation naturally produces this outcome, and the size limits are consistent with inflationary expectations. Another way to view these results is through probability. If the universe were only slightly larger than the observable region, it would be statistically unlikely for us to observe such extreme flatness and uniformity. The fact that we do observe them suggests a much larger universe. This probabilistic reasoning is part of how minimum sizes are inferred. It is not about absolute certainty, but about what is consistent with the data. It is also worth noting that these size limits apply to spatial extent, not to time. The universe could be infinite in space and finite in age. These are separate questions. Minimum size estimates say nothing about whether the universe had a beginning or whether time extends infinitely into the future. They also say nothing about what exists beyond the observable region in terms of structure or variation. The universe could be uniform beyond our horizon, or it could vary in ways we will never observe. From a practical standpoint, these minimum size estimates are as close as cosmology gets to answering the question, how big is the universe, beyond the observable limit? They do not provide a number that can be written on a diagram with a boundary. They provide a statement of scale. Whatever the universe is, it is not small. That conclusion is not philosophical. It is the outcome of multiple independent measurements converging on the same implication. The universe must extend far beyond the region we can observe by a factor that is already large and keeps growing as measurements improve. That is what scientists mean when they talk about minimum size estimates. They are not claiming to know the universe's full extent. They are showing, quantitatively, how much bigger than our cosmic horizon it must be. And that alone is enough to radically change how we think about our place in the cosmos. Inflation plays a central role in why scientists are confident that the universe is far larger than the observable region. Unlike later expansion driven by dark energy, inflation refers to a brief but extreme period of accelerated expansion that occurred very early in the universe's history. The key idea behind inflation is simple. In the first tiny fraction of a second, after the universe began expanding, space itself expanded exponentially. Distances doubled again and again in an incredibly short time. This was not a gentle stretching, it was a violent, rapid expansion that took regions once smaller than a proton and blew them up to astronomical scales. Inflation was not introduced to explain the universe's size. It was proposed to solve several problems that standard expansion could not. One of those problems was flatness. Without inflation, the universe's geometry would need to be fine-tuned at early times to appear nearly flat today. Inflation removes that tuning by stretching space so much that any initial curvature becomes negligible across observable scales. This is why the universe appears so close to flat. But that same mechanism implies something else. The observable universe is only a tiny fragment of the full space that inflation created. During inflation, regions that were once in causal contact were pushed far beyond each other's horizons. When inflation ended, only a small patch remained observable from any given point. That patch is what we now call the observable universe. The amount of inflation that occurred determines how large the total universe is compared to the observable region. A minimal amount of inflation would produce a universe only slightly larger than what we can see. More inflation produces a universe vastly larger. Observations allow scientists to constrain how much inflation must have occurred. The remarkable smoothness and flatness of the universe place lower limits on the duration of inflation. Those limits already imply a universe far larger than the observable horizon. Inflation also explains the origin of the tiny fluctuations seen in the cosmic microwave background. Quantum fluctuations were stretched by inflation to cosmic scales, becoming the seeds of galaxies and large-scale structure. The statistical properties of these fluctuations carry information about inflation's behavior. Measurements show that the fluctuations are nearly scale invariant as inflation predicts. This agreement allows researchers to rule out inflation models that produce insufficient expansion. Models that generate too little inflation would leave detectable curvature or unwanted features in the fluctuation spectrum. As a result, viable inflation models tend to produce a universe that is not just larger than the observable region, but vastly larger. Another important implication of inflation is that it makes the universe appear the same in all directions. Regions that now lie far apart were once close enough to reach thermal equilibrium before inflation stretched them away from each other. This explains why the cosmic microwave background has nearly the same temperature everywhere, even in regions that were never in causal contact after inflation ended. This isotropy is difficult to explain without inflation unless the universe is extremely small and finely tuned, which observations disfavor. Inflation therefore ties together several independent observations: flatness, isotropy, and the size of the observable universe. It also introduces a key asymmetry between what we can observe and what exists. The horizon is not a physical edge, it is the result of inflation stretching space faster than light could traverse it. Even if inflation ended long ago, its consequences persist. The observable universe remains bounded, while the total universe remains largely hidden. Some inflationary models go further and suggest that inflation may still be occurring in other regions, a concept known as eternal inflation. In these models, inflation ends locally but continues elsewhere, producing an enormous, possibly infinite multiverse. While eternal inflation is speculative and not directly testable, its existence would make the observable universe an infinitesimal part of the whole. Importantly, the size implications of inflation do not depend on eternal inflation. Even the most conservative inflationary scenarios, consistent with data, produce a universe much larger than what we observe. Researchers can estimate the minimum number of inflationary expansion steps, often expressed as e-folds, required to match observations. That minimum already implies extreme enlargement. Each additional e-fold doubles the linear size of the universe. Even a small increase in the number of e-folds leads to an enormous increase in total size. Because the physics driving inflation is not fully known, there is no strong theoretical reason to expect inflation to stop exactly at the minimum required. This makes a universe barely larger than the observable region seem unlikely. Instead, inflation naturally overshoots, producing a universe that is far bigger than necessary to solve flatness and horizon problems. This overshoot is not a flaw, it is a generic feature of inflationary dynamics. From the perspective of size, inflation is what allows cosmologists to say that the universe's total extent is not merely unknown, but likely vastly larger than the observable patch. Inflation also explains why attempts to detect global topology have failed. If inflation expanded space by a huge factor, any initial compactness would be stretched beyond detection. This makes a small, closed universe increasingly implausible in inflationary contexts. It is important to distinguish between inflation's predictions and what has been observed. Inflation predicts a large universe. Observations confirm the predictions that inflation makes about fluctuations and geometry. That consistency lends credibility to the size implications, even though size itself cannot be observed directly. Another subtle implication is that inflation decouples local observations from global properties. What we measure within our horizon tells us very little about the full universe's structure. Two observers in different regions of the inflated universe could see very similar observable universes, while being separated by distances far beyond any causal connection. This means that asking for the universe's real size may not even be a well-posed observational question. Inflation suggests that no single observer can ever access global information. Yet inflation still allows us to say something meaningful. Whatever the universe's total size is, it is almost certainly much larger than what we see. This conclusion does not rely on philosophical arguments. It arises from combining inflationary theory with precise measurements of cosmic structure. Inflation transforms the size question from one of direct measurement to one of inference. We infer the universe's vastness not by seeing it, but by understanding the physics that shape the part we can see. That is why inflation sits at the center of modern discussions about the universe's true scale. Without inflation, the observable universe's size would be puzzling. With inflation, its smallness relative to the whole is exactly what we expect. When discussions turn to the universe's real size, the word infinite inevitably appears. It is often used casually, but in cosmology it has a precise meaning and a limited role. Saying the universe is infinite is not the same as saying it is unimaginably large. It is a statement about geometry, not about scale in any practical sense. An infinite universe has no edges and no finite total volume. No matter how far you travel in any direction, there is always more space. This is compatible with several cosmological models, especially those with flat or negatively curved geometry. A finite universe, by contrast, has a total volume, even if that volume is enormous. Such a universe could still have no boundary if space wraps around on itself. Much like the surface of a sphere has no edge but a finite area. Observations cannot directly distinguish between an infinite universe and a finite universe that is vastly larger than the observable region. From within a limited patch, both look effectively the same. This is why claims about the universe being infinite are not observational conclusions. They are theoretical possibilities allowed by the data. Current measurements show that the universe's curvature is extremely close to zero. Flat geometry is consistent with an infinite universe, but it does not require one. A finite universe with a very large radius of curvature would also appear flat locally. This ambiguity is fundamental. No increase in observational precision within our horizon can fully resolve it. When cosmologists say the universe may be infinite, they are acknowledging this ambiguity, not asserting a fact. Another source of confusion comes from inflation. Inflationary models often produce extremely large or infinite spatial volumes. In some versions, inflation never ends globally, continuously generating new regions of space. In such models, the universe is not just infinite in size, but infinite in variety, as different regions could have different physical properties. However, inflation does not require infinity. It allows it. The distinction matters. Even if inflation occurred, the universe could still be finite, but enormous. The difference between finite and infinite lies beyond observational reach. From a practical standpoint, cosmologists focus on what can be constrained. They can rule out small, finite universes. They cannot rule out very large finite universes or infinite ones. This leads to a shift in language. Instead of asking whether the universe is infinite, researchers ask whether there is any evidence that it is finite and small. So far, there is none. Another point often misunderstood is that infinity is not a number. You cannot compare the observable universe's size to infinity in a meaningful quantitative way. Saying the universe is infinite does not mean it is bigger than any finite estimate in a measurable sense. Infinity is a qualitative property. This matters because popular explanations often imply that scientists are choosing between a large number and infinity. In reality, infinity is not something that can be measured or even approached through observation. All that can be said is whether finite models are compatible with data. Some finite models predict detectable features, such as repeating structures or correlations across the sky. These have been searched for and not found. That disfavors small, finite universes. But finite models with sufficiently large size produce no detectable features. Those remain viable. Another subtlety is that an infinite universe can still have a finite observable universe. Infinity does not mean everything is observable. Horizons still exist. Even in an infinite universe, light has had only a finite time to travel. The observable universe remains bounded by the age of the cosmos and the expansion history. This is why discussions of infinity do not change the observable universe's size. They only affect what may exist beyond it. Infinity also raises philosophical questions that science does not resolve. For example, in an infinite universe, every possible configuration of matter would occur somewhere, infinitely many times. This leads to paradoxes and interpretive issues. Cosmology acknowledges these implications, but does not rely on them. The science stops at what models allow and data constrain. Another important distinction is between spatial infinity and temporal infinity. The universe could be infinite in space but finite in time, or finite in space but infinite in time. These are separate questions. Most discussions of the universe's real size focus only on spatial extent. Current data favor a universe that is spatially flat. Flatness is consistent with infinity, but it is also consistent with a very large, finite universe. So when headlines say scientists have determined the universe is infinite, they are overstating the case. What scientists have determined is that there is no evidence for a small or moderately sized universe. The absence of evidence for finiteness is not evidence of infinity, but it makes infinity a natural option within the allowed models. Another reason infinity persists in discussions is that it simplifies theoretical reasoning. Infinite models avoid edge effects and boundary conditions that complicate equations. This does not make them true. It makes them convenient. Cosmologists are aware of this and treat infinity cautiously. It is a mathematically useful idealization, not an observational fact. The key point is that infinity and extreme largeness are observationally indistinguishable beyond a certain scale. Once the universe is much larger than the observable region, additional size becomes irrelevant to measurements. From our perspective, a universe that is 1 trillion times larger than the observable universe behaves the same as an infinite one. This is why minimum size estimates are more meaningful than maximum ones. They tell us how small the universe cannot be, not how large it is. Infinity represents the logical endpoint of that reasoning, not a measurable destination. So when scientists talk about the universe possibly being infinite, they are not claiming certainty. They are acknowledging that the data leave that possibility open. The real scientific progress lies not in declaring infinity, but in narrowing the alternatives. What has been ruled out is a universe that is only slightly larger than what we can see. What remains is a universe that is either extremely large or infinite. And from within the observable universe, there is no practical difference between the two. When scientists say they have calculated the universe's size, a natural question follows. How certain are these numbers? The answer depends on understanding where uncertainty enters the process and how much of it remains. The size of the observable universe is one of the most secure quantities in cosmology. It is derived from well-measured parameters: the age of the universe, the expansion history, and the physics of light propagation in an expanding space. Each of these inputs carries uncertainty, but those uncertainties are small and well characterized. For example, the age of the universe is constrained by multiple independent measurements. Slight shifts in the age change the observable universe's radius, but only modestly. The number does not swing wildly. Similarly, the expansion history is constrained by observations across many epochs. Early universe measurements, galaxy surveys, and supernova data all converge on a consistent picture. This reduces the chance that a hidden error is distorting the calculation. Because the observable universe's size is calculated by integrating these quantities over time, random errors tend to average out rather than accumulate catastrophically. This is why different teams using different methods arrive at nearly the same value. Uncertainty increases when scientists move beyond the observable universe. Minimum size estimates for the total universe depend on models and assumptions. Here, the confidence is not about a specific number, but about exclusions. Scientists are confident that the universe is not small. They are less confident about exactly how much larger it is. Curvature measurements provide a good example. Observations constrain curvature to be extremely close to zero, but they do not measure it exactly. There is always an error bar. That error bar translates into a range of possible universe sizes. Smaller sizes within that range are allowed. Smaller than that are ruled out. As measurements improve, the error bars shrink. This pushes the minimum size upward. However, there is a fundamental limit. Cosmic variance means that we only have access to one realization of the universe. Even with perfect instruments, some uncertainty cannot be eliminated. This places a ceiling on how precisely global properties like curvature can be measured. Another source of uncertainty comes from model dependence. Most size calculations assume general relativity is correct on cosmic scales. They assume dark energy behaves in a simple way. They assume inflation occurred. These assumptions are well supported, but they are still assumptions. If gravity behaves differently on scales larger than we can observe, or if dark energy evolves unexpectedly, conclusions about size could change. Scientists account for this by testing multiple models and seeing how robust conclusions are across them. The minimum size estimates tend to survive reasonable variations. This robustness increases confidence that the universe is genuinely large, not just an artifact of a specific model. Another uncertainty arises from how datasets are combined. Different surveys have different systematics. Combining them can introduce subtle biases if not done carefully. Modern analyses are explicit about these issues. They propagate uncertainties through the calculations rather than hiding them. This is why technical papers present confidence intervals rather than single numbers. Public summaries often omit these nuances, giving the impression of greater certainty than actually exists. There is also uncertainty in how future data might shift the picture. While dramatic revisions are unlikely, small changes in parameters could slightly adjust size estimates. Importantly, these adjustments are constrained. They do not open the door to a small universe. Another aspect of confidence involves internal consistency. Independent measurements of cosmic parameters must agree with each other. When they do, confidence increases. When they do not, scientists take the discrepancy seriously. The ongoing debate over the Hubble constant is an example. However, even this tension does not significantly affect minimum size estimates for the universe. This is because the horizon size depends on the integrated expansion history, not just the current expansion rate. So even unresolved tensions do not undermine the conclusion that the universe is large. Another factor is observational completeness. We cannot see beyond the horizon, so there is always a limit to direct verification. This is not a weakness unique to cosmology. Many scientific conclusions rely on inference rather than direct observation. The confidence comes from the convergence of evidence, not from a single decisive measurement. In the case of the universe's size, multiple independent lines of evidence all point in the same direction. That convergence justifies strong statements about what the universe cannot be. Where scientists remain cautious is in translating those statements into everyday language. Phrases like real size imply a level of finality that does not exist. Scientists are confident in minimum bounds and in the observable universe's scale. They are not confident in the total size in the sense of knowing its full extent. Another point often overlooked is that uncertainty does not mean ignorance. Knowing that something must be larger than a certain amount is meaningful knowledge. In everyday life, we rely on such constraints constantly. Cosmology operates the same way, so how confident are scientists? They are extremely confident that the observable universe's size is known to high precision. They are highly confident that the total universe is far larger than that. They are not confident that they know the universe's exact size, and they likely never will. That distinction matters. Confidence in science is not about claiming absolute certainty. It is about stating clearly what is known, what is ruled out, and what remains open. In the case of the universe's size, what is ruled out is smallness. What remains open is vastness on a scale that may never be fully quantified. And within that framework, the confidence is well earned. When people hear that the universe is much larger than the observable region, a natural reaction is to ask what exists beyond the horizon. Is it more of the same or something fundamentally different? The honest answer is that science cannot see beyond the horizon, but it can make informed statements about what is likely and what is constrained. The simplest assumption is that the universe beyond the observable region is statistically similar to what we see locally. This assumption is not arbitrary. It is rooted in the same physics that explains the uniformity and isotropy of the observable universe. Inflation predicts that space on very large scales should be homogeneous with small fluctuations superimposed. If that is true within our horizon, there is no obvious reason for it to suddenly change just beyond it. Under this assumption, beyond the horizon, there would be more galaxies, more cosmic structures, and more voids, arranged in patterns similar to those we observe. This does not mean exact repetition. The specific arrangement of galaxies would differ, but the statistical properties would be the same. This assumption is called the cosmological principle. It is a working hypothesis, not a proven fact, but it has passed every test within the observable universe. Another possibility is that conditions beyond the horizon differ in subtle ways. Inflation allows for this. In some models, different regions could have slightly different values of physical constants or different histories. These differences would exist on scales far larger than the observable universe, making them inaccessible to observation. From our perspective, such variations are indistinguishable from uniformity. More speculative models suggest that beyond our horizon, the universe could look radically different. In extreme cases, laws of physics could vary from region to region. These ideas are often associated with eternal inflation and multiverse scenarios. While they are mathematically consistent with some theories, they currently lack direct observational support. Science cannot confirm or refute these possibilities with present data. What science can say is that if dramatic variations existed on scales comparable to the observable universe, they would likely leave imprints. For example, large gradients or discontinuities could distort the cosmic microwave background. No such distortions are observed. This suggests that if variations exist, they occur on scales much larger than the horizon. Another question concerns whether the universe has an edge beyond the horizon. In standard cosmology, there is no physical boundary. The horizon is not a wall. It is simply the maximum distance from which light has had time to reach us. Beyond it, space continues. This is why the idea of an edge of the universe is misleading. There is no edge in the usual sense, just a limit to observation. Another issue is whether the universe repeats itself beyond the horizon. In a finite universe with certain topologies, it might. But as discussed earlier, evidence for such repetition is lacking. If the universe is finite, its repeating scale must be far larger than what we can observe. That makes repetition effectively irrelevant to our observations. And there is also the question of whether time behaves the same way beyond the horizon. Standard cosmology assumes it does. The laws governing expansion apply everywhere. Again, this assumption is supported by the consistency of observations across the observable universe. Another interesting implication of a very large universe is the existence of regions identical or nearly identical to ours. In an infinite or extremely large universe, random fluctuations will produce similar configurations somewhere. This idea often appears in popular discussions, sometimes exaggerated. While it follows mathematically, it has no observational consequences. Whether or not such regions exist does not affect physics within our horizon. Another point worth emphasizing is that what lies beyond the horizon is not frozen or static. Those regions have their own local histories and observers, each with their own observable universe. From their perspective, they are at the center of their own horizon, just as we are of ours. This symmetry is a fundamental feature of cosmology. The horizon also changes over time. As the universe evolves, some regions enter our observable universe, while others move beyond reach due to accelerated expansion. This means the set of regions we can observe is not fixed, even though it is bounded. Beyond the horizon, expansion continues as well. There is no special transition at the horizon itself. Another common misconception is that the horizon marks the limit of existence. It does not. It marks the limit of information. Information from beyond the horizon has not reached us and may never do so. That distinction matters because it clarifies what science is and is not claiming. Science is not saying that nothing exists beyond what we can see. It is saying that evidence from beyond that limit is unavailable. Given this, scientists rely on theory to extrapolate cautiously. Inflation, general relativity, and the observed uniformity of the universe all support the idea that beyond the horizon lies more of the same kind of space. Whether that extrapolation holds indefinitely is unknown. Another angle is whether future observations could ever reveal beyond the horizon. For light-based observations, the answer is no. The horizon is a fundamental limit. Other messengers, like gravitational waves or neutrinos, could probe earlier times, but they still face causal limits. No signal can outrun the expansion of space in a way that reveals arbitrarily distant regions. And this means that the question of what lies beyond the horizon may never be settled empirically. That does not make it meaningless, it makes it a boundary between science and speculation. Within science, the most conservative statement is that beyond the horizon lies more universe governed by the same physical laws, unless evidence suggests otherwise. So when scientists talk about the universe being far larger than what we can observe, they are not implying mystery realms or dramatic transitions just beyond view. They are describing a continuation of the same cosmic fabric, extending far beyond our observational reach. The horizon hides it, not because it is different, but because the universe has only had a finite amount of time to reveal itself. One of the most persistent misunderstandings about the universe's size comes from treating cosmic distances as if they behaved like distances in everyday space. When people hear numbers like 46 billion light-years, they instinctively imagine a sphere expanding outward into pre-existing emptiness. That picture is deeply misleading. In cosmology, distance is not a fixed backdrop. Space itself expands, and that expansion changes how distances accumulate over time. When scientists say the observable universe has a radius of about 46 billion light-years, they are not saying light has travelled for 46 billion years. Light has only been travelling for about 13.8 billion years. The larger number comes from the fact that space expanded while the light was in transit. This distinction is critical. It explains why naive calculations based on age alone fail, and it also explains why the universe can be much larger than intuition suggests. The misunderstanding often starts with the phrase light year. A light year is a distance, not a time. But when distances change over time due to expansion, the idea of a fixed distance becomes slippery. In an expanding universe, the distance between 2 points depends on when you measure it. Cosmologists therefore distinguish between several kinds of distance: proper distance, comoving distance, luminosity distance, and angular diameter distance. Each serves a different purpose. When discussing the size of the observable universe, scientists usually refer to comoving distance. This factors out expansion and asks how far away something is in a coordinate system that expands with the universe. Comoving distance allows researchers to compare positions consistently across cosmic time. If you ignore this and think in terms of static space, the numbers sound contradictory. How can something be 46 billion light-years away in a universe that is only 13.8 billion years old? The answer is that the universe was smaller when the light was emitted and larger when the light arrived. Another common misconception is that galaxies are flying through space away from us at enormous speeds. In reality, most distant galaxies are nearly at rest in their local space. It is space itself that is expanding. This matters for size discussions because it clarifies why distant regions can recede faster than the speed of light without violating relativity. The speed limit applies to motion through space, not to the expansion of space. As a result, parts of the universe can become permanently unobservable, even though nothing locally exceeds the speed of light. Another confusion arises from imagining the observable universe as something that grows into new territory. In one sense it does, but not in the way people imagine. The observable universe grows because light from increasingly distant regions reaches us. But those regions were already there. They are not newly created. This growth is about information reaching us, not about space being added at the edge. Similarly, when people ask whether the universe is expanding into something, they are importing everyday intuition into a context where it does not apply. Expansion does not require an outside. Space expands internally. Distances between points increase without needing a surrounding space. This is why questions like what is outside the universe are not well defined within standard cosmology. Another misconception involves assuming that the observable universe is centered on Earth or on our galaxy. It is not. Every observer, no matter where they are, has their own observable universe centered on themselves. The boundary is defined by the distance light has traveled to reach that observer. This symmetry is a direct consequence of homogeneity and isotropy. So when scientists say the observable universe has a radius of 46 billion light-years, they are not describing a special region centered on us in an absolute sense. They are describing a horizon defined by time and expansion. This also helps explain why there is no preferred center of the universe. Expansion looks the same from every location on large scales. Another misunderstanding involves confusing the observable universe with the total universe. Many discussions implicitly assume they are the same. They are not. The observable universe is the part we can see. The total universe includes regions beyond the horizon. This distinction is not semantic, it is fundamental. Failing to separate the two leads to false paradoxes, such as asking how the universe can be larger than the distance light has travelled. Once expansion is accounted for, the paradox disappears. There is also confusion about whether the universe's size is changing. The answer depends on what you mean by size. The proper distance to distant galaxies increases over time because of expansion. In that sense, the universe is getting bigger. The comoving size of the observable universe also increases, but at a decreasing rate due to dark energy. The total universe's size, if finite, could be constant in comoving coordinates while proper distances increase. These distinctions are rarely made in popular explanations, but they are essential for understanding what size claims actually mean. Another source of confusion comes from mixing up the particle horizon and the event horizon. The particle horizon defines how far light has already traveled to reach us. The event horizon defines how far light emitted now can ever travel to reach us in the future. These are different distances. The observable universe is defined by the particle horizon, not the event horizon. Failing to separate these leads to incorrect statements about what is or is not observable. For example, some regions we can see today will never send us new information beyond what has already arrived. They lie beyond the event horizon, but within the particle horizon. This nuance matters for interpreting statements about the universe's future observability. Another misconception is that better telescopes could eventually see the entire universe. This is false. No matter how powerful telescopes become, they cannot overcome the finite age of the universe and the expansion of space. Technology improves resolution and sensitivity, not causality. This means that the size of the observable universe is not limited by instruments. It is limited by physics. Another subtle misunderstanding concerns the idea of now across cosmic distances. In everyday life, now feels universal. In cosmology, it is not. When we observe distant galaxies, we see them as they were in the past. There is no single cosmic moment we can observe everywhere. So when people imagine a snapshot of the universe at a single time and ask how big it is, they are imagining something that cannot be observed directly. The size of the observable universe is defined in a specific coordinate sense, not as a literal photograph of everything at once. This also affects how we interpret expansion. We are not seeing galaxies move in real time, we are seeing a sequence of past states stitched together by light travel time. Another misconception involves the idea that expansion affects bound systems. It does not. Galaxies, solar systems, and atoms do not expand with the universe. Local forces dominate. This matters because it prevents misunderstandings like imagining people or objects being stretched as the universe expands. Expansion operates on large scales, not on local ones. People also sometimes assume that the universe's size must be something humans can eventually comprehend intuitively. It does not. Cosmic scales quickly exceed everyday intuition. Numbers lose meaning unless carefully defined. This is why cosmologists rely on mathematical descriptions rather than visual metaphors. Metaphors are useful for communication, but they often introduce errors when taken literally. Another recurring misconception is that uncertainty about the universe's total size implies that science knows very little about it. In reality, science knows quite a lot about what the universe cannot be. Knowing that the universe is not small, not young, and not highly curved is substantial information. Ignorance is bounded. Another confusion arises from treating all unknowns as equally plausible. In reality, some possibilities are strongly constrained, while others are merely logically possible. A universe only slightly larger than the observable region is not equally plausible as one vastly larger. The data disfavor the former. Understanding this helps avoid false balance in discussions. Finally, there is a misconception that cosmologists are constantly revising the universe's size by huge amounts. This is not true. The size of the observable universe has been stable for years. The refinements have been small. What changes is not the scale, but the confidence and the interpretation. As measurements improve, scientists become more certain about what lies beyond reach, even if they cannot see it. Understanding the universe's size therefore requires letting go of everyday spatial intuition and accepting a framework where distance, time, and expansion are intertwined. Once that framework is accepted, many apparent contradictions dissolve. The universe can be finite or infinite, young yet vast, bounded in observation but unbounded in extent. Those are not contradictions. They are consequences of how space and time behave on cosmic scales. As scientists push size estimates further, there is a natural temptation to ask whether the universe's size could ever be fully known. Not better constrained, not bounded from below, but actually measured in total. Modern cosmology gives a clear answer to that question, and it is not an optimistic one. There are limits built into the structure of the universe that no technology can bypass. The most fundamental limit is causal. Information travels at finite speed, and the universe has a finite age combined with accelerating expansion. These facts together guarantee that large regions of space will never be observable from here. Even if the universe stopped expanding tomorrow, light from sufficiently distant regions would still not have had time to reach us. Because expansion is accelerating, that barrier becomes permanent. This means that any claim to have measured the universe's total size would require access to information that can never arrive. This is not a practical limitation. It is a physical one. No future telescope, detector, or observational trick can overcome it. Another limit comes from cosmic variance. We only observe one universe, from one location. Even if we could see arbitrarily far, we would still be sampling a single realization of cosmic structure. That limits how precisely global properties can be inferred. In statistics, this is equivalent to trying to determine the full properties of a population from a single data point. You can rule out extreme cases, but you cannot fully reconstruct the whole. This is why cosmology relies heavily on probability and confidence intervals, rather than definitive statements. There is also a limit imposed by inflation itself. Inflation smooths out information about initial conditions. It erases details about what came before and replaces them with near uniformity plus small fluctuations. This is a feature, not a flaw. It explains why the universe looks the way it does. But it also means that inflation hides information about the global structure of the universe. If inflation lasted long enough, it wipes out observable traces of topology, boundaries, or edges. The better inflation works, the less information remains about the universe's total extent. This creates a strange inversion. The same mechanism that allows us to explain the universe's observed properties also prevents us from learning its full size. Another limitation comes from theoretical degeneracy. Many different global universes can produce the same observable patch. A finite universe with a huge radius, an infinite flat universe, and certain curved universes can all produce indistinguishable observations within our horizon. There is no observational test that can uniquely pick between them. This is not a temporary gap in knowledge, it is a permanent degeneracy. Even perfect data would not break it. Another issue is that size itself may not be a well-defined global quantity in all models. In some cosmological solutions, space does not admit a single global measure of size that is meaningful across all times. In such cases, asking for the universe's total size is like asking for the total distance of a line that has no endpoints. The question assumes something that may not exist. This does not mean cosmology is incomplete or incoherent. It means that not all intuitively appealing questions correspond to physically meaningful ones. Science is good at answering questions that can be framed in operational terms. How far can light travel is operational. What is the total size of everything that exists? May not be. This distinction matters because it reframes expectations. The goal of cosmology is not to satisfy every intuitive curiosity. It is to describe what can be tested and constrained. Another reason total size may be unknowable is that the universe could be infinite in a way that is not distinguishable from extreme largeness. No finite observation can confirm infinity. Infinity is not something you detect. It is something you fail to rule out. So even if the universe is infinite, there will never be an observation that confirms that fact. At best, observations will continue to fail to find boundaries. This asymmetry makes infinity scientifically awkward. It is compatible with data, but not testable in a decisive way. The same applies to many multiverse scenarios. If other regions exist beyond our horizon with different properties, their existence may have no observable consequences here. In that case, they remain outside the domain of empirical science. This does not mean such ideas are meaningless. It means they occupy a different category, theoretical possibilities rather than observational conclusions. Another limit comes from the nature of measurement itself. Cosmological measurements always involve modeling. You do not directly measure curvature or expansion history. You infer them by fitting models to data. This introduces unavoidable dependence on assumptions. As long as multiple models fit the data equally well but imply different global sizes, the total size remains underdetermined. No amount of data within the horizon can fully eliminate that underdetermination. There is also a temporal limitation. We observe the universe at one moment in cosmic history. Some global properties might become easier or harder to infer at different times, but even if we waited indefinitely, accelerated expansion would eventually isolate us further, not less. In the far future, observers will have access to less information than we do today, not more. This means that the present era is unusually favourable for cosmology. If the universe's total size cannot be determined now, it likely never will be. Another point worth making is that this limitation is not unique to size. Many global questions share the same fate. We may never know whether time is infinite, whether the universe repeats, or whether physical constants vary elsewhere. Cosmology provides a framework for understanding what can be known and where the boundaries lie. Those boundaries are part of the science, not a failure of it. It is tempting to interpret these limits as disappointing, but they are better understood as clarifying. They tell us which questions admit scientific answers and which do not. In the case of the universe's total size, science can say a great deal about minimum scale, geometry, expansion, and structure. What it cannot do is deliver a final number for the total extent of everything that exists. That is not because the universe is too mysterious, it is because the laws that govern it place limits on what information can ever reach us. Those limits are themselves among the most profound discoveries of modern physics. They reveal that knowledge has a horizon, just like light does. And beyond that horizon, questions may still be meaningful, but answers are no longer observational. When all of this is stripped down to its core, the story of the universe's size is not really about a number. It is about how cosmology has changed its relationship with scale itself. For most of human history, the universe was assumed to be small, static, and centered on us. The idea that it might be vast existed philosophically but not scientifically. There were no tools to anchor such claims to measurement. That changed in stages. First came the realization that the universe is expanding. That alone forced a rethink of size because it tied distance to time. The universe was no longer a fixed container. It was dynamic. Then came the discovery of the cosmic microwave background, which anchored the observable universe to a specific physical event. For the first time, the universe had a measurable horizon rooted in early universe physics. That allowed scientists to calculate how large the observable universe is with real confidence. After that came precision cosmology. Measurements stopped being rough and started being tight. Parameters like curvature, matter density, and expansion history were no longer vague. They were constrained. With those constraints in place, cosmology crossed an important threshold. It became possible not just to measure what we see, but to rule out what we do not see. That is the real shift behind claims about the universe's real size. Modern cosmology does not claim to have found the universe's boundary. It claims to have excluded entire classes of universes that were once plausible. Small universes are gone. Moderately sized universes are disfavored. What remains are universes that are vast beyond intuition, whether finite or infinite. This is a different kind of knowledge than people often expect. It is not cartographic, it is structural. We do not know how far the universe goes. We know how constrained its geometry must be, how smooth it must be, and how much expansion must have occurred. From those facts alone, size follows as a consequence. Another important shift is how cosmology now treats ignorance. Unknowns are not treated as blank spaces to be filled with speculation. They are treated as regions fenced in by constraints. The universe's total size sits inside such a fenced region. We do not know where the far boundary lies, or if it exists at all, but we know it cannot be nearby. That is not a philosophical statement. It is an empirical one. This framing also changes how cosmologists think about progress. Progress does not always mean discovering something new to look at. Sometimes it means proving that something cannot be there. In this case, progress means demonstrating that the universe cannot be compact, cannot curve sharply, and cannot wrap back on itself at accessible scales. Those exclusions are permanent unless the underlying physics is wrong. Another subtle shift is in how central the observable universe has become. It is no longer treated as a rough estimate of the whole. It is treated as a carefully defined region with precise physical meaning. That clarity allows scientists to separate questions cleanly. How big is the observable universe? That is answered. How big is the total universe? That is constrained, but not measured. Confusing those two leads to most misunderstandings in public discussions. Modern cosmology keeps them distinct. Another consequence of this shift is humility. The universe is not just large, it is structured in a way that prevents complete access. This is not because humans are limited, it is because causality is. Even a hypothetical civilization with perfect technology would face the same horizon. That realization reshapes what it means to know the universe. Knowledge is local, not global. We infer global properties indirectly through consistency and absence of contradictions. That method works remarkably well, but it has limits. Another important takeaway is that the universe's size is not a standalone property. It is entangled with expansion, geometry, inflation, and dark energy. You cannot change one without changing the others. This interdependence is why claims about size have become more confident over time. As each piece was measured more precisely, the allowed space for size narrowed. This also explains why future discoveries are unlikely to shrink the universe dramatically. To do so would require rewriting multiple independent observations at once. That kind of revision is possible in science, but it leaves traces. No such traces are currently visible. The most likely future is not a new cosmic scale, but a refinement of constraints and language. Scientists will become more precise about what is meant by size, extent, and universe. Public language may lag behind, but the technical picture is already stable. Another lesson from this story is that intuition is not a reliable guide at cosmic scales. The universe violates almost every spatial instinct humans have. It is older than distance suggests, larger than light travel implies, bounded in observation but unbounded in extent, centered nowhere and everywhere. These are not paradoxes. They are consequences of relativistic space-time. Cosmology has learned to live with them by abandoning everyday metaphors when they fail. The phrase "the universe's real size" feels intuitive, but it hides a mismatch between human expectation and physical reality. There may be no single real size in the way people imagine. There may only be an observable size, a minimum size, and an open-ended beyond. That is not vagueness, it is precision about what questions make sense. In that sense, modern cosmology has not just calculated distances, it has clarified the structure of ignorance. It has drawn a sharp line between what can be known, what can be constrained, and what may remain forever inaccessible. That line is one of the most important results in all of science, because it tells us that the universe is not just vast in space, it is vast in what it allows us to know and in what it permanently withholds. Watch the next video.